Welcome students. In the last few videos, we have seen about photoelectric effect, right? Compton effect, de Broglie's concept and uncertainty principle. Okay, all these four factors come into what is known as wave particle duality. Okay, so before entering into the actual wave mechanics, starting with Schrodinger wave equation, let us go through some typical problems, okay, in all these four aspect topics like photoelectric effect, Compton effect, right, de Broglie concept and Heisenberg's uncertainty principle, the problems which are commonly appearing in all the competitive exams in India. Okay, we'll just go through some typical problems and then enter into quantum mechanics. Okay, now look at this first problem on photoelectric effect. The threshold wavelength of potassium is 558 nanometers. Okay, that is lambda naught for potassium is 558 nanometers. When monochromatic light of lambda equal to 400 nanometers is incident on it, okay, the stopping potential will be, so remember Einstein's photoelectric equation, okay, right, K maximum equal to h nu minus phi, okay, right, K maximum is equal to EV. So EV, a stopping potential, is equal to, in terms of wavelength, it will be hc by lambda, mu equal to c by lambda minus 5a. Work function is hc by lambda naught. Okay, right, bring that e to this side. Hc by e value, if you simplify and substitute, I told you the relation between the energy and wavelength is energy in electron volts, okay, is equal to 1240 by lambda. If lambda is in nanometers, right, 1240 by lambda will directly give us energy in electron volts. Okay, so I'll take lambda, the wavelength of light incident is 400, so it is, right, 1240 by 400 nanometers is hc by lambda minus hc by lambda naught. I can take it as 1240 by 558 nanometers given. That will directly give us the energy in electron volts. From that, stopping potential can be found. What is 1240 by 400? It is 124 by 40, right? 43s are 120, right? 4 point, it becomes 40. So it will be 3.1, okay, electron volts minus 1240 by 558. What is 1240 by 558? Okay, if calculators are allowed in the exam, well and good. If calculators are not allowed, we have to do it, okay, manually. Now, what is 1240 by 558? I'll take like this, 1240 by, instead of 558, I'll go for a round figure, 560. Doesn't matter much, the error will not be much. Okay, so it is 1240. Okay, 124 by 56. 56 twos are, okay, how much? 112. 12 will remain, 120 again, 56 twos are around roughly 2.2. But remember here, I have increased the value slightly from 558 to 560. Means the actual value, if I put 558, it will be slightly more than 2.2. It may be around 2.3 also. Okay, so whatever it is, 3.1, right, 3.1 minus 2.2. How much it is? Around 0.9 volts. Now look at the options which are very close to 0.9. Okay, I have increased the value from 558 to 560. Okay, so right, the actual value will be slightly more than this, 2.3 something I'll be getting. So around slightly less than 0.9 will be the right answer. Now look at the options which is less than 0.9, very slightly. The first option is 8.88. No, okay, 0.88. It is very close to our 0.9. So right, this becomes our what you call the option or answer. Okay, right, 88.8, 2 point, they are very far off. What is very close to our 0.9 volts? It is 0.88. Okay, very simple, straightforward problem which has appeared in one of the Central University entrances. Okay, so the second problem is, a metal surface is illuminated by light of two different wavelengths, 248 nanometers. Okay, 248 nanometers and 310 nanometers. The maximum speed of photoelectrons corresponding to these wavelengths are U1 and U2. If the ratio of U1 and U2 is 2:1 and Hc equal to 1240 electron volt nanometer, the work function of the metal is nearly. Okay, another straightforward question here. So work function of the metal as before, right? What do we do? It is 1240 nanometers, means 1240 by lambda will directly give us the energy. Okay, energy is related to EVS, that is stopping potential. Okay, so he's asking for the work function of the metal here. Okay, now how do we proceed? U1 by U2. Okay, U1 by U2 is given as 2:1, or U1 equal to 2U2. This is what is being given. Next one, two wavelengths are also given, work function phi. So what is Einstein's general equation? Okay, right, K maximum, kinetic energy maximum, equal to h nu minus phi. Okay, that is, right, half m, right, U1 square is equal to h nu minus phi. He has not given any frequency, he has given us wavelengths. Okay, the first wavelength is right 248 nanometers, second one is 310 nanometers. Okay, for 248 nanometers velocity is u1, maximum velocity is u1. For 310 nanometers maximum velocity is u2. They are in the ratio 2:1. Okay, so with this information we'll proceed further like this. Okay, so I'll read this as what? hc by lambda 1 minus phi. Okay, this is half m u1 square. Similarly, half m u2 square is equal to hc by lambda 2 minus phi. Work function will be same for the given metal. Okay, lambda 1 is given 248 nanometers. Okay, and u1 and u2 are related as what? u1 equal to 2u2. Okay, so half m, half m. Okay, they get cancelled. Okay, if I divide, or okay, let us not leave it like that. Now what do we do? Okay, half m u1 square, u1 equal to 2u2. So put u1 equal to 2u2, that is 4u2 square it will be. So half m 4u2 square, okay, is equal to hc by lambda 1, that is nothing but 1240 by lambda 1 is 248 nanometers minus 5. Okay, right, that is 4 into half m u2 square is equal to, right, 1240 by 248 minus 5. The second equation is, right, half m u2 square equal to, right, 1240 by the second wavelength given is 310 nanometers minus 5 days. Okay, right, now what is 1240 by 248? 250 5s are 1250, 248 5s are 1240. So this is nothing but 5. Similarly, 1240 by 310. Okay, 310 4s are 4 3s are 12, 4 10s are 40, 1240. So this is exactly 4, this is exactly 5. Okay, the problem is has been simplified here. So 4 into half m u2 square is equal to, right, 5 minus 5, and what you call half m u2 square equal to 4 minus 5. Okay, now you simply divide these two equations. Half m u2 square, half m u2 square will get cancelled. Okay, that is 4 is equal to 5 minus 5 by 4 minus 5, or if you think cross multiply, 16 minus 4 5 is equal to 5 minus 5. Okay, so take this 4 5 to the other side and bring that 5 to this side. Okay, 16 minus 5 11 equal to 4 5 minus 5, it is 3 5, or 5 equal to 11 by 3, 11 by 3, 3 3s are 2. Okay, roughly around 3.7. So phi equal to 3.7 electron volts. Okay, so see which option is given close to 3.7. Okay, the first option is 3.7, 3.2, 2.8, 2.5. We are getting around 3.7. So the option is 3.7 electron volt. Photoelectric effect supports quantum nature of light because. This is a theoretical question. He has given 4 options. What is the first option? Photoelectric effect supports the quantum nature of light because. Why photoelectric effect is a solid support for quantum theory of light? Means there is a specific wavelength, there is a specific frequency, okay, mu naught, below which photoelectric emission stops. Okay, there is a specific frequency mu naught below which okay, right, there is a specific frequency nu naught below which photoelectric emission stops. Yes, okay, this is one of the 4 salient features of photoelectric effect, right? There exists a threshold frequency nu naught below which photoelectric emission stops. Okay, only when the incident light's frequency is above that mu naught, equal to or above that mu naught, photoelectric emission is occurring. Okay, because according to quantum theory, E equal to energy of each photon equal to h nu. The binding energy of the electron inside the metallic surface is work function is written as h nu naught. So right, h nu great minus h nu naught will give you the maximum kinetic energy of photoelectrons. Okay, so unless nu is equal to nu naught or nu greater than nu naught, right, photoelectric emission cannot occur. So there is a specific frequency nu naught below which photoelectric emission stops. This option is a correct option. Okay, next one, the K maximum of photoelectron depends only on the frequency and not on incident intensity. According to quantum theory, according to classical theory, more intensity means more energy, but according to quantum theory, more intensity means more number of photons. Okay, that's all. Okay, but energy of each photon remains as h nu only. Unless you change the frequency, energy of photon will not change. Unless the energy of the photon changes, okay, kinetic energy of photoelectrons will not change. So, right, the K maximum photoelectron depends only on the frequency and not on intensity. Okay, K maximum equal to h nu minus phi. This is anyway work function, a constant for a given metal. So when you increase frequency, K maximum increases. When you decrease frequency, K maximum decreases. It does not depend on intensity. Okay, what depends on intensity? Right, photoelectric current depends on intensity. Okay, so the second option given is also a correct statement. Right, the third option is even when the surface is faintly illuminated, photoelectrons leave the surface immediately. We have seen the fourth salient feature as what? There is no time loss in the process. The moment light falls, right, photoelectrons are found to come out, right? Why there is no time loss? Because it is an interaction between 2 different particles. One particle is the electron, other particle is the incident light photon. Okay, so because it is a particle-particle interaction, right, transfer of energy from one particle to another particle is instantaneous. So that's why, right, whatever may be the intensity of light, even if you send light from a small bed lamp also, that faint light will go and fall. If the energy of each photon is more than the binding energy of the electron or more than the work function of the metal, right, immediately the electron will come out. Okay, so even when the surface is faintly illuminated, photoelectrons leave the surface immediately. This option is also correct. Okay, right, all these 3 options are supporting the quantum nature of light only. Okay, electric charge of photoelectrons is quantized. That is the 4th option. Okay, now this has nothing to do with what you call photoelectric effect. The charge of an electron is quantized, has nothing to do with supporting quantum nature of light. Okay, right, so the 4th option is not a valid one. So the first 3 options A, B, C, right, are valid options. So this is a multiple choice answer question type. Okay, so what are the options here? You have to put all 3 options A, B and C. All 3 are correct. Okay, that's why if we say photoelectric effect and Compton effect have proved the quantum nature of light beyond doubt. Okay, right, so this is one problem. We'll see the next problem. Right, graph is given, is asking some questions about it. Okay, the following figure shows the graphs of stopping potential Vs and 1 by lambda nanometer inverse for 3 metals 1, 2 and 3. Okay, for 3 metals 1, 2 and 3, the 3 graphs are like this. Okay, this is metal 1, this is metal 2, this is metal 3. Okay, 1 by lambda in nanometer inverse is 0.001, that is 0.002, 0.004. From there onwards, okay, as 1 by lambda is increasing means what? Lambda is decreasing. Okay, if the wavelength is less than the threshold wavelength lambda naught, photoelectric emission, right, occurs, and what you call the kinetic energy of photoelectrons keeps on increasing. Stopping potential will keep on increasing. That's why the graphs are like this. And one more thing we have to keep in mind, all the 3 lines given are parallel to each other, I mean their slopes are also slopes will be equal. Okay, so this is the graph given, right? If phi1, phi2, phi3 are the work functions of the three metals respectively, then he is asking the questions. Okay, what are the four options given, right? He is asking us the ratio of phi1, phi2, phi3 as 1:2:4, or phi1 phi2 phi3, 4:2:1. Slope of each graph is hc by e. Slope of each line is hc by e. UV light will eject electrons from the metals 1 and 2, but not from the metal 3. Okay, which of these four options, right, is correct or are correct? We have to see now. Okay, now look at this picture. Okay, look at this graph here, right? This is the threshold wavelength for which we are taking inverse here. Okay, work function ratios is asking. In general, what is work function? Work function phi1 is, okay, work function is in general phi equal to hc by lambda. Okay, work function. So phi1 equal to hc by lambda 1, that is nothing but hc into 1 by lambda 1. Okay, 1 by lambda 1 is given as 0.001. Okay, right, 1 by lambda 2 is given as 0.002. 1 by lambda 3 is given as 0.004. Okay, so phi1 is 2, right? Phi2 is 2. Phi3 equal to hc are common for all, it's a constant. So 1 by lambda 1, that is 0.001, is to 1 by lambda 2, that is 0.002, is to 1 by lambda 4, that is 0.004. Means they are in what ratio? 1:2:4. So phi1 is to phi2 is to phi3, they are in the ratio 1:2:4. This first option is correct. So second option obviously will not be the correct one, so we can remove it. Okay, the third option given is, okay, slope of each graph is hc by e. Okay, the stopping potential versus frequency graph, right? How do you write photoelectric equation? EVS equal to, right, hc by lambda minus phi. Okay, or Vs equal to hc by e into lambda minus phi by e, we'll write. Okay, right, now we are taking this as this in which form, right? Vs equal to hc by e into 1 by lambda minus phi by e. Okay, right, so this equation is of the form what? This equation is the form y equal to mx minus c form. Okay, so vs we are taking on the y-axis, 1 by lambda we are taking it on the x-axis. So the coefficient of 1 by lambda becomes the slope m here. So hc by e is the slope of that graph. Okay, because all three lines are parallel, they'll have equal slopes. So every line has slope of hc by e. So this option also will be correct. Now the fourth option is UV light will eject electrons from metals 1 and 2 but not from 3. Okay, any light should emit electrons from the metal plate, means the wavelength should be less than the threshold wavelength. Okay, so what are the threshold wavelengths? Threshold wavelengths he has not given, but he has given 1 by lambda threshold wavelengths he has given. Okay, reciprocal of threshold wavelength he has given. What is that? 1 divided by, it is like this. Okay, 1 divided by 0.001 nanometer inverse, means 1 by 001 nanometers nothing but 1000 nanometers. 1000 nanometers means how many angstroms? Okay, 1 nanometer equal to 10 angstroms. So it is 10,000 angstroms. Means wavelength less than 10,000 angstroms can cause photoelectric emission from that metal. This is for the first metal. For the second metal, 1 by lambda value is given as 1 by 0.002 nanometer inverse. That is 1 by 0.002 will be, right, half of this, that is nothing but 500 nanometers. Okay, 1 by 0.002 will be 500 nanometers, that is nothing but 5000 angstroms. Means from second metal, if you want photoelectrons, the wavelength of incident light should be less than 5000 angstroms. Okay, for the third metal, okay, 1 by lambda value is 0.004. Okay, so 1 by 0.004 lambda value will be how much, right? See, this is half of this, this will be half of this, that is around 250 nanometers. Okay, that is around 2500 angstroms. 2500 angstroms. Okay, means if the incident light's wavelengths are less than these values, wavelength values, then only, right, those metals can show photoelectric effect. is saying that UV light photons means what? Wavelengths less than 3000, less than visible light is UV light. Okay, visible light wavelengths are from 3500 to 7000. So UV light photons means less than 3500. Usually UV light means in our minds it will be 1000, 2000 angstroms. It will be 1000, 2000 angstrom, 3000 also. So anything less than 3500, here 10,000. So happily UV light can cause photoelectric emission from the first metal. Okay, it can cause emission from the second metal also. Okay, but UV light means, right, UV light will eject electrons from 1 and 2 but not from 3. Okay, right, if the wavelength is 3000 angstroms, it cannot emit photoelectric effect, it cannot show photoelectric effect. But if the wavelength is less than 2500, UV light photons can have wavelength less than 2500 also. So right, it can cause photoelectric emission. Means what? Third metal, UV light cannot eject electrons from the third metal. This option will be wrong. Okay, right, so this options are right, first and third options are correct, second and fourth are wrong in this problem. Look at this fifth problem in photoelectric effect. For photoelectric effect with incident photons of wavelength lambda and stopping potential Vs, identify the correct variation of Vs with lambda. Means how the stopping potential varies with lambda. He has given 4 graphs. Okay, which graphs are correctly drawn? That's what he's asking. Okay, Vs is the stopping potential and 2 graphs are given with respect to lambda, 2 graphs are given with respect to 1 by lambda along x-axis. Okay, so the moment we see stopping potential lambda, the photoelectric equation variation is, right, EVS equal to, right, Hc by lambda minus phi. That's how we write. This is work function. Okay, right, that is Vs equal to Hc by E into 1 by lambda minus phi by E. Minus phi by E. Okay, so stopping potential, this is in which form? Y equal to mx minus c form, that is a straight line with a negative y-intercept. Okay, so instead of x we have 1 by lambda, for y we have stopping potential. So stopping potential versus 1 by lambda graph will be sorry, a straight line with a negative y-intercept. Okay, which of these graphs you see? This is not a curve. This is a curve actually. So this graph cannot be, the variation between Vsn by 1 by lambda cannot be a curve. It should be a straight line. Okay, so this is a straight line with a negative y-intercept. With a negative y-intercept. So this graph is correctly depicting Vs versus 1 by lambda graph. This straight line with a negative y-intercept is the correct one. Okay, and what about the variation stopping potential with lambda? Vs is inversely proportional to lambda. Inverse proportionality will be a curve like this. It cannot be a straight line given. It should be a curve like this. So, right, the first graph is the correct graph between Vs versus lambda. Vs versus lambda will give you a curve with negative slope here. Okay, Vs versus 1 by lambda will give you a straight line with a negative y-intercept. So the options A and C are correct in this question. Okay, right, now we'll see some problems in COMPTON effect. Okay, so this is a problem in COMPTON effect. Okay, separate COMPTON effect experiments are carried out using visible light and X-rays. Okay, if the scattered radiation is observed at same scattering angle, then see, usually in theory of COMPTON effect we have seen COMPTON effect is mostly done with X-rays. Okay, why don't we do it with visible light? Also that we have seen in that COMPTON effect video, because percentage change in wavelength will be small. Okay, at any given angle the change in wavelength will be independent of the wavelength. Okay, d lambda will be independent of lambda. Means whether you send 1 angstrom wavelength, the change will be it will become 1.5. Okay, even if you send 1000 angstroms also, 1000 will become 1000.5 only. That 0.5 change will remain same at a given angle. Okay, now the question is, experiment is done with what you call visible light and X-rays. Visible light and X-rays. Okay, if the scattered radiation is observed at same scattering angle, then X-rays have greater shift in wavelength and what you call greater change in energy. What is the expression for Compton shift? Compton shift is d lambda equal to h by m naught c into 1 minus cos theta. At a given angle, d lambda is constant. It is independent of lambda. Okay, so right, the first option, X-rays have greater shift in wavelength and the greater change in photon energy, is wrong. Okay, whether you send visible light or X-rays, d lambda, there is no lambda expression in d lambda, lambda term in d lambda. Okay, so the first option is wrong. The two radiations will have same shift in wavelength lambda, but X-rays have greater change in photon energy. Okay, the two will have same shift in lambda is correct only, but X-rays have greater change in photon energy. See, if d lambda is more, d nu is more. Okay, if d nu is more, d energy also will be more. It is not like that both will have same change in wavelength, but X-ray photons have change in energy is meaningless. Okay, so second option also is not correct. First option is anyway wrong. Okay, the third option is the two will have same shift in lambda, but visible light photons have greater change in energy. Okay, that is also not correct. Okay, when wavelength shift is same, energy shift also should be same. So third option is also wrong. The two will have same change in wavelength and same change in photon energy. Okay, this option is the best option, correct option. Okay, the two will have, because in Compton effect, d lambda is independent of the incident wavelength. Okay, so when change in wavelength is same, change in frequency also will be same, change in energy of the photons also will be same. Okay, so the option here is D. The next problem in Compton effect is, it is like this. An experimenter, a scientist has observed about 1.5% change. Okay, scientist has observed 1.5% change, right, when in Compton effect. Okay, he has observed 1.5% change in Compton effect. Okay, at a scattering angle of 120 degrees. Okay, right, he has observed the Compton shift d lambda to be 1.5%. okay, when the scattering angle is 120 degrees. Okay, then what is the incident wavelength? Means incident lambda is asking, incident wavelength. Okay, means what are the given? Scattering angle theta is given here. Okay, 1.5% change in Compton shift means d lambda equal to 1.5%. Okay, so how do we proceed? What is lambda is asking? So how do we proceed? Lambda dash minus lambda is equal to d lambda equal to, we have h by m naught c into 1 minus cos theta. H by m naught c into 1 minus cos theta. H by m naught c is known as Compton wavelength, I told you. Okay, what is the value of Compton wavelength? Right, 0.0242 angstroms into 1 minus, what is scattering angle? 120, cos 120. Okay, cos 120 can be taken as cos 90 plus 30. Cos 90 plus 30 is minus sin 30. Sin 30 is half. Minus half minus, it will be plus half. Okay, that is nothing but, right, 3 by 2 into 0.0242 angstroms. Okay, this is d lambda. How much is d lambda? 1.5%. That is, lambda dash is 1.015 lambda minus lambda. Okay, shift is 0.115% means lambda dash is 1.015 lambda. Okay, incident wavelength is lambda. Okay, how much is this equal to? 0.015. Okay, this will be 0.015 into lambda equal to 3 by 2 is 1.5 into 0.0242 angstroms. Okay, therefore lambda equal to 1.5 into 0.0242 angstroms divided by 0.015. Okay, 1.5 by 0.015 is 100. 100 into 0.0242 angstroms is 2.42 angstroms. That is 0.242 nanometers. This is the incident wavelength lambda. Incident wavelength lambda. When observed at a scattering angle of 120 degrees, the percentage change in wavelength will be 1.5%, and the observed wavelength will be, right, 1.015 into 0.242 nanometers. Okay, this is a previous TFR question, I think, some time back. Okay, right, 0.242 nanometers. Decent, good question. This one is okay. In the next video also, we will solve some problems related to, we have already seen photoelectric effect and Compton effect. We'll solve some more problems in de Broglie's concept of matter waves and uncertainty principle, right? Then we'll enter into quantum mechanics. Okay.